Okay, so we've been through all the components of the Earth's atmosphere. Now we're going to get to the fact that the atmosphere is an example of an ideal gas and an ideal collection of gases. So this slide says, in case you were wondering, all of the gases that are in the Earth's atmosphere, the nitrogen, the oxygen, the argon, the carbon dioxide, the water vapor, all of them have masses. And gravity pulls down on mass so that air has weight. You might not think about air having weight, but actually air is heavier than you can possibly imagine. The total mass of the atmosphere is 5.5 quadrillion tons, and still that's only 1/1,000,000th of the Earth's mass. So air definitely has weight. That weight that we have has some qualities that are called ideal. So when I gave the list of all of the descriptions of the atmosphere, the last one I gave to you was that it's ideal. Now I'm going to explain what ideal means in physics. Ideal in terms of gases in physics refer to the fact that you could have an atmosphere filled with many different types of gases and none of them would interact with any of the others. Kind of like a pool table, when you shoot a pool stick, all of the balls go flying off in all directions. None of them stick together. None of them interact with each other. They just bounce off of each other. In the same way, all of the different gases in the atmosphere bounce off of each other, don't interact with each other, and as a result, they don't bond with each other, and they have some really interesting qualities that we can calculate in mathematical equations. Don't be too scared. Like I said, these billiard balls do not interact with each other. This nitrogen and oxygen are independent. And in looking at that, it's kind of like shooting a pool ball. These gases have no bonds at all, and they are independent pressures. You could have a pressure for nitrogen, a pressure for oxygen within the entire atmospheric pressure. They have independent quantities and volumes, and they have just one average temperature for the entire thing. So the atmosphere is kind of like the pool table, and the gases are the billiard balls that are zooming around on the pool table. As a result of that, we can look at those properties of pressure and temperature and volume, and we can manipulate them and analyze them a little bit more clearly to understand how to forecast weather better. Just a short review. Remember, pressure is weight over area, and weight is mass times gravitational acceleration. Okay? Keep that in mind. Pressure is a force. The weight over an area is a force. And when we look at the behavior of gases in terms of pressure and volume, this is what they get. Think about yourself breathing in and holding your breath. You've just expanded the volume of your lungs. You've expanded the surface area inside your lungs. Previously, they had been a bit contracted. As a result, you have now greater area in the denominator of this pressure equation. It's going to make the pressure in your lungs lower. When you breathe in, the pressure of your lungs goes down. Now, I hear you that I breathe in air and air has weight, so that really messes up the whole equation. The weight that you gained by the breath in was less important and less measurable than the expansion of the area that your lungs underwent. So this area becomes a more conclusive measure, and it impacts pressure more. So we say that when volume goes up, pressure goes down. Okay? Keep that in mind. We're going to look at that a little bit. How is that volume and pressure going to impact our meteorology? Here's a scenario. The barometer is dropping all day long, and you've got to get a weather balloon up in the air for local measurements. You decide to underinflate the balloon just a bit. Why do you do that? you're obviously thinking that it's going to inflate more when it's up in the atmosphere. But let's see why. As that balloon ascends, it encounters lower gravity, and that starts two big changes. With less gravity up at altitude, there's less pull on the molecules that are inside your balloon. Those molecules inside your balloon have less compression around them from the atmosphere around them. And less compression at that altitude means that there are fewer molecules above that altitude to compress down more. And the more air is above a level, the greater the squeezing effect onto that level. So at altitude, I haven't got a whole lot more up there because I've lost so much of my gravity, and I haven't got much pushing down on my little weather balloon. Less compression inside the balloon means that the molecules inside the balloon are going to collide and zing back and forth like the billiard balls with more force. They push on the balloon walls, they expand them, and the volume of the balloon increases. So by underinflating it, I'm actually preparing for the expansion when it hits lower gravity. Because when the volume of a balloon expands, the surface area of the balloon expands. And since pressure is weight over area, that means the pressure is going to decline because the area that expanded is in the denominator. So it cuts the dividend off and makes it less. So when volume goes up, pressure goes down. The underinflation was designed to prevent the popping as the balloon expanded. Let's talk about another quality of the gases, temperature, and relate that to pressure. Think about hot tires on a hot summer day. Remember from our first lectures, temperature is the measure of kinetic energy of movement. When that mercury expands in heat, it expands and goes up the temperature gauge. So with hot tires, when the temperature increases, the kinetic energy of the molecules inside the tire increases. The molecules become accelerated, and since weight is mass times acceleration, that means the weight goes up. And since weight over area is pressure, that means the pressure goes up. So all in all, when temperature increases, pressure increases too. That's Charles's law, and it's why your tires blow out on hot summer days. Let's think about temperature and pressure and meteorology. How does air pressure impact temperature in the atmosphere? Okay, you have to put up, let me take this over here, you have to put up another weather balloon. Now the temperature is dropping, and you blow up your balloon and overinflate it just a bit this time. Why would you overinflate it in cold weather? As that balloon ascends, it encounters lower temperatures. And that makes sense because there's less gravity high up, there's less compression, there's less forceful collisions, so there's less volume to that balloon, and there's less kinetic energy in that balloon, and so you have lower temperatures in that balloon. Cold contracts. So the overinflation prepared for less volume. When the pressure goes down, well, when the temperature goes down, the pressure goes down. Okay. And that's the end of that. I'll see you on the other side for buoyancy.